Hi, my name is Bruce Margetti from the Society of Tribologists and Lubrication Engineers. In the following video, we will speak with Kyle Roget from the University of North Texas. He will be talking about his student poster presentation from the 2012 annual meeting titled Molecular Dynamic Simulation of Frictional Behavior in FCC Copper and HCP Magnesium. Welcome, Kyle.
I did a molecular dynamic simulation of FCC copper and HCP magnesium. The reason for doing this was to see similarities and differences between the two structures, between HCP and FCC, and to see the similarities and differences in mechanisms and how coefficient is affected through velocity, temperature, stress concentration, so on and so forth. So for copper, we did two orientations. We did 100 on family of planes with the 100 directions, and then we also did the 111 planes with the 110 direction. And you can definitely see similarities with macroscopic scale, where coefficient of friction for 111 is definitely lower than the 100 due to it being a close-packed plane. With the various velocities, you actually see a decrease from 1 to 15 meters per second, and then you get an increase, which is shown in this area, where the dislocation density and the coefficient of friction both decrease, but when it gets to the plowing regime, you get the adhesive and plowing component instead of just the adhesive component. We looked at effective simulation size, small simulation size, which means how many atoms are in your simulation. We looked at anywhere from 200,000 up to about 2 million atoms to see if actually having the coefficient, will the coefficient of friction actually decrease with these different simulation sizes. And we didn't see, it seems that we can actually use the small simulation size to decrease computing time, so that's something nice for us. And then we looked at magnesium, and we did prismatic and basal planes. Definitely the basal planes we've seen that have lower friction than the prismatic plane, which is seen experimentally. You can actually see in the prismatic planes, you can actually see wear particles forming at higher velocities. So to conclude this, we see that coefficient of friction is lower for the 111 as compared to the 100 planes. For magnesium, it's lower for the basal than it is for prismatic. Structural defects and surface energies affect the coefficient of friction at the atomic scale. Future work, we want to look at the stress distribution within the bulk of the material underneath the tip to see how and where dislocations form. Is it in the critical result shear stress regime? And then we also want to include temperature and see how temperature affects the microstructure at the surface and farther down into the bulk.
Thank you, Kyle. If you have any questions, you can reach Kyle at kyleroget@yahoo.com. Also, you can find more videos like Kyle's by visiting the STLE website at www.stle.org.